Finding the absolute maximum from an equation is a little bit more involved. However, it's really very similar to finding a relative maximum. There's just one extra step. So finding absolute extrema from equations. This will be very similar to finding relative extrema, but you need to check the y-coordinates of the relative extrema and the endpoints. Once you do that, you can compare the y-coordinates to see which is actually the most extreme value. So let's do a problem. Find the absolute maximum of f of x equals negative 3x to the fifth plus 5x cubed. Now we know we're talking about any maximum, we're talking about f of x, so that means our answer line is going to be increasing, decreasing. And if we're working with an equation, that means that we have to be working with a plus minus line. Plus minus, the f prime is what translates into f of x being increasing, decreasing. F prime of x, check. So now I need f prime. We know that f of x equals negative 3x to the fifth plus 5x cubed. So that means f prime of x is going to be negative 15x to the fourth plus 15x squared. We can factor. Let's factor out negative 15x squared. So that's going to give us x squared right there. We factored out a negative, so this is a minus 1. We can factor that further. X plus 1, x minus 1. If you factored it with negative x squared plus 1 and positive 15x squared, you'll still get the same answer. You'll just have everything reversed from what I'm doing here. Okay, negative 15x squared equals 0 when x equals 0. X plus 1 equals 0 when x equals negative 1. X minus 1 equals 0 when x equals positive 1. We can put those up on the chart. And now if we have a very negative number, this negative 15 is always negative. X squared is always positive. Negative 2 plus 1 is negative. Negative 2 minus 1 is negative. That's 1, 2, 3 negatives. So this is negative overall. Between negative 1 and 0, negative 15 is always negative. X squared is always positive. Negative, let's say 0.5 plus 1 is going to be positive. Negative 0.5 minus 1 is negative. That's positive overall. Between 0 and 1, negative 15 is negative. X squared is positive. Positive 0.5 plus 1 is positive. Positive 0.5 minus 1 is negative. Still positive overall. Greater than 1, we've still got our negative and our positive right here. 2 plus 1 is positive. 2 minus 1 is positive. Negative overall. Let's translate that. Decreasing, increasing, increasing, decreasing. Okay, so we're looking for the absolute maximum of f of x. So looking here, we have something for f of x that comes down like this, goes up, and then comes down like this. And I actually forgot part of the problem. This should be on the interval -2 to 3. Otherwise, we can't really find an absolute maximum. So this is -2, this is 3. Okay, my bad. So, if our function goes like this, then we have a potential absolute maximum right here. That's the relative maximum. But we also could have a potential absolute maximum right here. Maybe what happens is that it starts off, f of x starts off really high, comes down, goes up, comes down. So the actual highest point is over on this endpoint here. So what we have to do now is we need to check, let's do this in blue, we're going to find f of -2, which is one potential absolute maximum. We're going to find f of 1, and we're going to compare them to see which is really the largest. It's kind of as if these are in a little boasting match. I'm the maximum. I'm the maximum. No. Well, let's check and see. So we have a possible absolute maximum at x equals -2 or x equals 1. So let's find them. F of -2. Here's our equation. -3 times -2 to the 5th plus 5 times -2 cubed. It's -3 times -32 plus 5 times -8. So this is 96 minus 40. It's 56. Compared to f of 1, whoops, there we go, which is -3 times 1 to the 5th plus 5 times 1 cubed. So clearly this is larger. The absolute maximum of f of x on the interval -2 to 3 is 56 when x equals -2, because f of -2 is greater than f of 1, and all other points are less than one of these. Let's do another one of these for practice. Find the coordinates. So that's x and y of the absolute minimum of f of x equals 3x times e to the -x on the interval 0 to 2. Okay, minimum f of x. That means it's f of x, it's an increasing, decreasing line. Working with equations, so we translate that to plus minus, and the translation is f prime of x. So that means we need f prime. These are being multiplied together, so we're going to use the product rule. Derivative of the first times the second plus the first times the derivative of the second Remember, this has to have the chain rule because it's not just an x up there. Okay, we can do some factoring here. This factors out to be 1. There's a little x left over. That never happens. X equals 1. So, we can make our sign chart. Over on this side, this is always positive. Let's say we've got 0. 1 minus 0 is also positive. Over on this side, 3e to the negative x is always positive. 1 minus, let's say 2, that's going to be negative, so it's negative overall. Translating that, we've got increasing and we've got decreasing. So notice there's a relative maximum here. We're asking for the absolute minimum. And I did it again. I need to stop at 0 and stop at 2 because otherwise we can't find it. But I did put it in the problem this time at least. So what this means is it means that we have potential absolute minima right here and right here because that's where f of x starts increasing or stops decreasing. So now we have to find f of 0 and f of 2 and compare them. Three times 0 times e to the 0, well, this is all multiplied together and one of them is 0. So f of 0 clearly equals 0. And then for f of 2, that's 3 times 2 times e to the negative second power. So if we work with that negative exponent, 3 times 2 is 6. We don't know exactly what this value is without a calculator, but we do know that this is definitely positive. That is definitely 0. 0 is less than all positive numbers, so this is smaller. So this means the coordinates of the absolute minimum of f of x on the interval 0 to 2 are 0, 0, because f of 0 is less than f of 2, and all other values are bigger than these.